Hi, my name's Afro Electronic. You can call me Afro. I've decided to make a series of videos by which I'd explore and maybe rediscover some of the fundamentals of music and share it with you, and then hopefully that way we can all be inspired if we took a different way perhaps to look at music, particularly because synthesizers allow us so much more accessibility and functionality. Maybe we can now afford to imagine if we took just a tiny little different look at music. Okay, so in that case, if you agree with me, let's take a look at our first topic. Now, why don't we try and reimagine or explore counting? And you'll then say to me, counting, what does that have to do with music? Well, counting helps us to identify possibilities. Counting helps us to know, if we've taken a look at every possible thing, maybe what we might like, what we might not like. So I'll give you an example. I came across a really nice FM synthesizer, and FM synthesizers come with algorithms that are preset. And I find myself asking the question, how do I know that all of the possible algorithms affordable by this synthesizer have been given to me? And in order to do that, I had to know how to count all the possible algorithms that synthesizer was able to make. Whatever we're counting, those things belong to a group. And in mathematics, we call those groups sets. Anything can be any group of things can be a set. You could have a set of people, or you could have a set of apples. And within sets, we usually find we have subsets. So for example, within your set of friends, you could have friends who are male. Within your set of apples, you could have apples that are green. There's a male subset within your set of friends, and there's a green apple subset within your set of apples. Similarly, any other color of apples within that set of apples also make their own subset. Okay? So now we know that what we're counting belongs to a set, or there could be a subset within that set, and we want to know how many of them there are. Okay, so for example, with my FM synth, I could say how many possible two-carrier algorithms can I get within this synthesizer. Does that make sense now? Okay. Right, so let's start with the definition. What is counting? To understand counting, you've got to understand quantity, because what we call counting in every language is giving an accurate number and matching it to a right quantity. So for example, this quantity here can be matched with the number 2. Okay? When we allocate number to quantity, we call that enumeration, which is what you would call counting. If someone said to you, how many pens are there in that cup? You might list them all and match them to a number and say 25. Okay? That's enumeration. But then, how do we approach this? Because if you could look at two sets and automatically in your mind know which of them is smaller. You say, you go to the supermarket, you want to know what queue you're gonna go join. You don't have to count. You usually have to count how many people are in the queue. You simply look at the two queues. One of them is shorter than the other. You get an idea of quantity, and you join which one you'd rather join. Okay. Similarly, you could take a look at the number of bananas in a bowl, and there could be 5 of them, and you just go 1, 2, 3, 4, 5. That's fine. So what other kind of counting is there? Well, sometimes a set can have a number of things in it that we are aware of, but we can't count it all because either we don't have time or it's just not obvious to us. But we need to know how many of them there are. I'll give you an example. And this is a very familiar one. Most people are familiar with the concept of the lottery in the UK. So you've got 59 numbers, and you're asked to pick a subset of 6 of those numbers. How many possible ways can you pick a subset of 6 numbers from 59? And I need to explain a bit of a caveat here. In this situation, I'm talking about a scenario where the set 1, 2, 3, 4, 5, 6 is considered the same as the set 1, 3, 5, 2, 4, 6, i.e. order does not matter. Why don't you try listing all the possible subsets of 6 numbers from a list of 1 to 59, and I'll catch you after a break because I want to talk to you now about some other projects that I do. Right, so if you want somewhere in Manchester to come and try out the skills that you've discovered, like we talked about in the video, or if you want somewhere to come and just try out your music, I host a really cool electronic music open mic night called Space Noodle Manchester. I've put a link down below. Just click on it. I've also put the Instagram of Space Noodle Manchester below, so you can just click on it and find out where we are in Manchester. The venues do change, but usually are pretty much the same. And also, what I do like to do is not just leave you with a video, right? I like to develop resources that support what we've done, and you can go check them out on Patreon. It's patreon.com/supportafro. And whilst you're there, I'd really appreciate your support as well. So, let's get on with the video. Alright, so how did that go? Remember, before the break you were going to go away and see how many possible subsets of 6 numbers you could get from a set of 1 to 59. And yeah, I was being a bit cheeky, I do admit. I mean, there are so many of them. There are about 45 million of them, right? The accurate number is actually going to be somewhere on the screen above me now, right? And I worked out that in order to list and match them, you remember the traditional way of counting? 5 bananas, 1, 2, 3, 4, 5. If you decided to list all those subsets, it will take you 18 months if you did 1 a second. And then you have to count them, because listing is not the same as counting. I assume you're not going to list them at the same time. So it'll take you 36 months, 1.5 years, to list all 45 million of those subsets. Again, 45 million is me rounding up. But check this out, right? We did that saying order doesn't matter. If we bring order into matter, then it's about 32 billion subsets. Now, again, it'll take you about 1,024 years to list them all, and I'll give you another 1,024 years to count them, and that's assuming you did 1 a second. So yeah, you would have to be alive at about the time of, I don't know, Archimedes, Plato, to do it all. But I've managed to do it all in 3 minutes, and this is the beauty of what we're doing here. Right? We can explore and discover all these huge scapes, massive amounts of things in very little time. So how do I do it? Well, let's get to it. Okay, let's start with a much smaller example. Imagine we've got 3 discs, red, blue, green, and we've also got 3 spaces in which to slot these discs. The question is, how many ways can I slot them into those discs? I.e., I could do red, blue, green first, or green, blue, red, etc., etc. Now, how will I know how many of those different ordered sets there are, but also how will I know that I've got them all? Right, well, think of it like this. Forget about which one you pick first, just pick one first and think to yourself, how many places do I have to put this one in? Okay, there are 3 possible places to put them in. Now, to help visualize a little bit, I'm going to draw, right, those 3 possible outcomes. Now, it's really important to remember that these are possible outcomes. So, in real life, if you had to pick a disc and put it somewhere, you wouldn't see all the 3 possibilities, but I'm going to draw those 3 possibilities for us now, okay? So, here's the first one. Think of them as 3 parallel universes. Here's our second universe, and here's our third. Okay, and then for the sake of example, let's assume that we picked the red one first. Okay, you pick your disc, it's a red one. Okay, in each of these worlds, these universes, you've got 3 possible ways. So you could go, okay, you could go there this time, you could go there this time, you could go there this time. So there are 3 possible ways. And then you think to yourself, well, in each of these worlds, there's going to be a second trial, because we want to now place the second one. How many ways are there to place that second one? Well, let's create for each of these, again, 2 parallel universes. Okay. Okay, so, but we're going to replicate each of these because we did start off with, oh, that's blue. We did start off with a red there. We started off with a red, okay? And in this one, red, red, and red, red. Okay, let's say the second one that we picked was blue. I've got the blue already. You can see that in each of these outcomes, for each of them, I've only got 2 places to put my blue. Okay, so here I could put blue there, and then blue there, and I could go blue, and then blue, and here blue, and then blue. And we see that in every single possibility or outcome, I've only got 1 place to put my green, and here it goes, green, 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 which tells me that if I want to place 3 things into 3 places, paying attention to the order in which I place them, well, I could place the first one in 3 ways. And for each of those 3 ways, there are 2 ways to place the second one. And for each of those 2 ways, there's only 1 way to place the third one. 3 times 2 times 1, which is 6 ways. And there we go, 3, 4, 5, 6 ways. Okay? But this example is quite special, and I've chosen it deliberately because it does pay attention to order, and also it lets us think, well, if you had 4 things to place in 4 places, would it be 4 times 3 times 2 times 1? Yes, it would. If you had 5, would it be 5 times 4 times 3 times 2 times 1? Yes, it would. Okay, so we can generalize and see if we had n things to place into n places, paying attention to their order, the number of ways we can do that is n times n minus 1 times n minus 2 all the way down to 1. Okay, now for a few definitions, okay. The mathematicians like to call this 3 times 2 times 1, they call it 3 factorial. I'll write it here. 3 factorial. But we don't like to write out this factorial word all the time, so we give it a symbol and it looks like this. 3 factorial equals that. It looks like that, like 3 with an exclamation mark. Okay? So we can generalize now and say that the number of ways to place n things into n places, paying attention to order, is n factorial. So let's bring it back to the music, shall we? The fun bit. If I say to you, how many ways can I arrange 4 things into 4 places? You now know that's 4 factorial, which happens to be 4 times 3, which is 12, times 2, 24, times 1, 24. So 24 ways. Well, this is the thing, right? So consider, say, a pentatonic scale. Okay? I'm going to start off with, say, C, the key of C. I've got C, D, E, G, A. Right. But between these notes are intervals. Okay? I know that there is a tone between C and D. There's another tone between D and E. And there are 3 semitones, which is called a minor third. So I don't know how to write that, I just made this up. So I'm just going to write 3 with a small m, minor third, and then there's a tone between G and A. And this subset of intervals create what's called the major pentatonic. Okay, so it's important to just focus on these intervals. You could start at any note. Okay, just the intervals are important. And then there's also the minor pentatonic. Okay, and that looks like, if you start with C, it starts like C, then E flat, then F, then G, then B flat. Again, we don't need to worry about what the notes are, we just need to know that the interval between C and E flat, that is a minor third. Yeah. And then we've got a tone, another tone between F and G, and another minor third between G and B flat. So in the line of what we've been talking about, I want to focus on these subsets. So there are 4 of them, and I would say to you, right, so if I want to discover something new, if I want to be inspired by something new in the pentatonic scale, how many possible ways can I arrange these intervals? Now you know that that's 24 ways. I'm not going to list them all here, but if you were to go to my Patreon page, I've got the resources up there for you so you can see all how they're listed. When I look at something like that, I've got 24 steps, then what I can do is I can feed in all those intervals into a sequencer, any sequencer. I use the Octatrack as a MIDI sequencer. And then just listen to it over and over again and feel inspired. What does it bring out to you? How does it sound? You know, it's going to be 25 steps. What can you do with that? Or maybe you can even use a smaller subset of those 24 possible intervals. And the same for the minor pentatonic as well. So hopefully we've explored today, we've discovered something, and now hopefully when you go and put this into practice using your sequencer, you'll be inspired. Okay? Alright, and this bit is for those of you who are watching and might be perhaps a bit more experienced with mathematics, because I know what you're thinking. You're thinking, well, Afro, fine, but what if I had 3 discs? But say I have more spaces to put them in. I have 5 spaces to put them in. How does that work? Well, let's start again paying attention to order, right? Well, if I had 5 spaces, I could choose 5 ways to put the first one, right? And then each of those 5 ways gives me 4 ways to put the second one. And each of those 4 ways gives me 3 ways to put the third one. Okay, fine. That doesn't look like an n factorial or anything, does it? Okay, well, no it doesn't. But we want to express everything in terms of factorials because that's what we're used to now. Well, I can do a little trick, and this is a little trick, because in mathematics we know anything divided by itself is itself, right? So I'm going to complete this factorial, but I'm also going to divide by this. So 2 times 1. So if you look carefully, this is 2 factorial. I'm going to write this down. This is like, so this is 5 factorial, right? We agree. Over 2 factorial. But 2 is 5 minus 3, right? And we already started off with 5 in the first place. So I can write this as 5 factorial over 5 minus 3 factorial. Okay? So if I started with n places for R objects, the number of ways that I can arrange those R objects in n places is, well, n factorial over n minus R factorial. And that's paying attention to order. But you're still not going to let me go, are you? You're not going to let me go because you're going to say to me, well, yes, what you've done there solves my problem if I want to arrange them, i.e. I pay attention to order. What if order doesn't matter? Because Afro, when you started the video, you talked about the lottery problem, and in the lottery problem, order did not matter at all. So, go on then Afro, let's give us the whole thing so we can solve the lottery problem. And you need to get back to your 45 million, remember? Okay, we can do that too, but I need to go back to what we did before, okay? Right, so you'll remember that if we had to order 3 things in exactly 3 places, there would be 6 ways of doing that, which is 3 times 2 times 1, or 3 factorial, right? But if you look at this, these 6 outcomes here, you will notice that the reason that they're different, actually the only reason that they're different, is because we've ordered these disks differently for each of them. But so the question says, what if order did not matter? If to order them, you have n factorial ways, if order did not matter, i.e. if blue, green, red was the same as red, green, blue, which is usually what happens when you pick from a subset. You pick things and you go, oh, I picked red, green, blue. It doesn't matter if you picked green, blue, red, or if you picked red, green, blue. They're the same because that's what you picked. So that, where order doesn't matter, we call a combination, because order doesn't matter. So how many combinations can you get given a known set of arrangements? And by the way, in mathematics, we call the number of arrangements permutations. The only way I can think of remembering it is that mutations change. So when you change, because the order is changing, it's a permutation, okay? Well, if there are n factorial permutations, then to just get back to the number of combinations, just divide by n factorial. In this case, you'll see it equals to 1. If you said to me, how many different combinations can you get from red, blue, and green if you picked all 3 of them at the same time? There's only one, because each of these permutations has only red, blue, and green in it. So there's only one way. But that is not always the case. It's not always 1 for everything. Because what if I had 5 places to put 3 things? We already worked out earlier that the number of permutations would be 5 factorial over 5 minus 3 factorial. But that's the number of permutations. Order matters. So for me to get the number of combinations where order doesn't matter, I need to divide by 3 factorial. I'll generalize in a minute, but let's take a look at what this means. If I had n places to put R objects, then the number of permutations, so order matters, is equal to n factorial over n minus R factorial. Yeah? The number of combinations, so order doesn't matter, that is n factorial over n minus R factorial times R factorial. Okay? But you're going to say to me, well, so when order doesn't matter, it's a combination, and when order matters, it's a permutation, why is my bike lock called a combination lock? That's because the word combination is much more familiar to most people than the word permutation, and it makes it easier to sell bike locks. That's why. But really, technically, well, mathematically, if we're talking mathematics, being true to mathematical definitions, they are permutation locks. But don't go try and ask people for your permutation lock, because they just won't get it, okay? Right, so here we are. And I think this is pretty much like where I wanted to get to, that the way of permuting n objects, R objects into n places, is n factorial over n minus R factorial. And the way of combining, or the number of combinations that you can get from R objects in n places, is n factorial divided by n minus R factorial times R factorial. But I really do want to come back to, now that we've generalized, that lottery problem. Now you'll agree with me that on lottery night, when the numbers come up if the numbers come up 1, 5, 3, 4, 2, 6, what happens at the end? They rearrange them into order, 1, 2, 3, 4, 5, 6. And it doesn't matter in which order you put them on your ticket, as long as you get those numbers, you're going to win. So really, what we're looking at with the lottery is combinations, the number of combinations, okay? So now we've got 59 numbers, think of them as 59 spaces, and we want to fill them in with 6 objects, okay? How many possible ways can we do that? Well, that would be 59 factorial, because that's my n. My r is 6, and 59 minus 6 is 53. If you do that, you'll get about 45 million. And that's why the answer is 45 million. But interestingly, in America, their lottery pays attention to order, because you have to play a date. So I'll leave you to go away and think about the likelihood of winning the American lottery. I hope this has been inspiring for you. I really do. If you have enjoyed what I've done, if you think it's been worth your while, then please go to Patreon and sponsor me so I can make more videos. Also, here on YouTube, you can click on the subscribe button, and you can even like the video, share it with your friends. I intend to make lots more videos like this, really to focus on how these kinds of perspectives can help us to explore and rediscover the fundamental concepts of music, and also be inspired to make new and more music. So thanks again for watching, and I'll catch you on the next one.